Let's start. For sequential logic design problem, you have to implement some sequential digital circuit using the logic gates and standard components. There are already some logic elements which you can find available in the left side design plane. For example, if you go to the memory, there are D flip-flop, T flip-flop, JK, so some other things which you can directly use. But for today's work, we're going to use the logic gates, and we will build up the sequential circuit with all these logic gates that we have available under the gates and some wiring. We will try to understand the basic design consideration for the sequential circuits, like how to avoid race condition, that sort of stuff. We will also try to standardize the design so that we can create a reusable circuit design pattern from the standardization and reusability perspective. We will also apply design patterns to organize the basic I/O and peripheral circuitry. We will do all these things using the Logisim Evolution version 3.7.2. If you use a different software or a different version of Logisim, the options might appear differently to you. We'll also try to understand and get ourselves familiarized with the basic sequential circuit blocks. We'll also try to read the datasheets for industrial components or ICs that we have as part of the design activity. More details about the design problem can be found in Maurice Manner's book, which is available in our library. We have two problems, and for these two problems we will have 2 weeks of duration. So the deadline will be 2 weeks after you get this PDF. For problem 1, you have to design a system which is under the car company. So you are working in a car company and it is trying to launch system like Apple CarPlay or Android Auto that will connect to any mobile phone that the driver uses. They name this service Car Connect, and Car Connect have a dedicated button in the dashboard. This button allows the driver to easily connect and disconnect using the Car Connect system. The description of the problem and specification given is something that states, when the Car Connect button is pushed, it should start the Car Connect. Pushing this button for the second time should stop the Car Connect. The button also incorporates a built-in green LED which glows when the Car Connect is operating and remains off otherwise. The switch signals the car's main control logic to turn on the electromechanical system that is used to run the Car Connect. So you have this description that there is a push button which will be used, and using this push button we have to implement a Car Connect like interface in the Logisim. So once you press the button, the Car Connect should be turned on. If you do not press the button, the Car Connect state should remain the same. So you asked your colleague about how to get started, and they suggested you that you can use some type of switch. For this particular case, they suggested to use SPST-NO switch, which is essentially single pole, single throw, normally off switch. And then we have this switch, and lots of other switch can be explained in this link. So if you go to this link, there are single pole, single throw, single pole, double throw, and some other switches. So we were talking about the switch which is single pole, single throw. So there are different types of switch. You can study more from this link here. So for the activities, you have to find what is the meaning of this SPST and NO in the context of the electromechanical switches. You have to write down the truth table or the state diagram or the state table for the next Car Connect state CT+1 as a function of the current push button and the current Car Connect state CT at time t. So essentially you have to design a truth table for this sequential logic design. Then you have to design the small digital circuit with Logisim using this basic logic gate. So you are not allowed to use the flip-flops or some other memory components. So when this circuit is used with the chosen switch, it will make the circuit function as a toggle switch. Use the button component in Logisim for this question. Input output. Under input output you should see a button here. There is a button that you can use. So the circuit should function in a way that as long as you keep the button pressed, an LED or the output signal will stay on. When you release the button, then the LED or the output signal goes off. Design a toggle switch such that when you press the button once, your LED turns on, and when it remains on until the button is pushed again. You have to show which 74XX family ICs can be used to implement this circuit. You have to write down the pin number of the aforementioned ICs that will be used by your circuit. Finally, you have to show a timing diagram for the aforementioned circuit showing all possible transitions of push button and car connect values. So this is the first problem. For the second problem, you have to solve a problem of addressable I/O for your car company. Imagine your car company has asked you to design a circuit to implement an addressable I/O for a 4-bit microprocessor. This will be used, that is, this addressable input-output interface will be used to activate 7 actuators, which is an AC compressor, 4 individual door locks, and the engine starter and windshield wipers. This circuit will allow a CPU with 4-bit addresses to activate actuators by placing or writing suitable address on the address bus. The specification is provided. The AC compressor is turned on by putting a binary equivalent of 0 and enabling the I/O enable line. The address value of 2 gets the second door locked. There is a small sketch here. You can see it's a 4-bit microcontroller. There is the I/O enable control line and the 4-bit address bus. Here is the I/O control circuit, and the actual actuator control lines are output from this I/O control circuit. For this problem, we want you to detail out the I/O control block and generate the required gate level circuitry for it. For the moment, you can ignore the internals of the microprocessors. So here is the incomplete truth table that you have for the output actuator operation. So as you can see in this truth table, you have address bus line, some 4-bit lines, A0 to A3. We have an I/O enable line which can have 0 to 1, and the actuator control lines are one for AC, 4 for the doors, D0, D1, D2, D3, engine starter and wiper. So we have in total 7 actuator control lines. Some functions are given. For example, when we have the I/O enable 0, then all the IOs are disabled. So no matter what we have in the address bus, we don't care, nothing will happen because the IO is disabled. So all the actuators should get 0. And then we have, if the IO is enabled and address bus line contains all zeros, then also we should not update anything and nothing will happen. If the IO enable is 1 and then we have some values, for example, if we have all zeros in the address line, then the AC should be turned on. Similarly, if IO enable is 1 and we have 1 in the A0 bit and all the other bits are 0, which means we have written 1 as a value in the address bus, the door 0 should get locked. So we have this incomplete truth table for the actuators. Your colleague has also given you some timing diagram. A timing diagram is essentially a diagram that contains a clock cycle. So it has a clock which shows different ages. For example, you have a 0 age, like rising age, a falling age, and the clock is essentially some sequential device that generates pulse at a constant rate. So you have 0 pulse and then one high value, 0, 0, high. So we have some circuit here which will complete a cycle after some certain time. So we can use this clock. We have an IO enable line. It shows all the IO enable lines on different part of the time. We have all the address buses. These are our input lines. And then we have the actuator lines. So here we have actuator lines. So at any time when we change the IO enable, whenever we have a rising edge, so here we have a rising edge of the clock, the circuit is triggered. This can be done other ways also, but for this particular scenario we have a rising edge trigger. So we can have rising edge triggered circuit, we can have falling edge triggered circuit, we can also have both edge triggered circuit. But for now, after we have a rising edge, the values will be changed. So for example, we have here 4 bits of address or 4 inputs, and we have one input which is IO enable line. So whenever we change the IO enable line and make it high, that is we make the IO enable on, only after that whatever the address bit was, depending on that we should have some activities in the actuators. For example, the AC actuator is activated once we have all the zeros and IO enable to be high. So when IO enable is high, after that at the rising edge we have AC also turned on. Similarly, the AC remains on even if the IO enable button gets 0, because we should not change anything after we have seen this at IO enable 0. At the next stage, when we again have the rising edge where IO enable is 1 and some address bits are written, for example we have written A1 here, that means we have written 2 in this point, so we have A1 to be high and A0 is always 0. We have all the other specifications working as it is, so it should have the corresponding values updated. So the door sensor, the door actuator gets updated because that's what given here. So door 0 gets locked when we have IO enable 1 and some specifications. Finally, we have our transitions, like when the IO enable is disabled and bits are changed, correspondingly we will update our time. You have to design and verify the required circuit to implement the IO control subsystem. Note that a given way does not specify a way to turn off the device once it has been turned on. Making appropriate assumptions, you have to include a control sequence that can also allow to turn off a device. So you need to complete the truth table with some assumptions where you can have the doors closed or open, AC is off, something like that. You have to show a timing diagram that shows the change of states of the various signals and control lines implemented by your circuit. Show the clock and set of pattern waveforms or A0 to A3 and the control lines based on the following activity, where you have clock cycle 1, A3 to A0 values are 0010, at clock cycle 3, A3 to A0 values are 0001, at clock cycle 5 we have some other value, at clock cycle 8 we have some other value. So you have to show a timing diagram of at least 8 clock cycles. This is what you have to do for this lab.